So thank you everyone for joining us here on the AI Hardware Show Aftershow party. This is after episode 1, where we've spoken about Google, NVIDIA, IBM, Biren, AMD, and the EdgeQ.
Yes.
So the purpose of these after-show specials is let's just talk about the chips. What you saw in the previous episode was our scripted format. This is more casual.
More casual.
More casual. Even more casual than we were.
Even more casual.
This episode is sponsored by IBM. Did you realize that IBM is in AI hardware? If you didn't, then you should be watching more of this channel. Don't forget to like and subscribe. But we'll hear more about IBM later in the episode. So my name's Ian Cutress. This is Sally Ward-Foxton. You should know us if you actually watched the episode. Links in the description below. Don't forget to like and subscribe. You know, all that jazz, bollocks, whatever. So with this, what I want to start with is the purpose of this series, right? I came to Sally with an idea to create this series about AI chips. There are so many AI chips in the space. I mean, yeah, just...
There's literally hundreds, too many to keep up with at this point, and it's my full-time job to study these, and there's still more that I discover all the time.
You know, small ones that just happen to be in Taiwan and, you know, just have one use case and, yeah, and so it's, even since we've been discussing this for a few months now, and it seems like every week we're now emailing each other. Have you heard of this company? Have you heard of that company?
Yeah, have you seen this? Have you? Oh,
yeah.
We are losing a few at the same time as well, though. So
we're
starting to. That's starting to happen, which is sad but necessary, I think.
We're going to cover those in a future episode of the main show. But to kick things off with this first episode, I wanted to go over some of the main chips in the market, things that perhaps people are more familiar with, and then a couple that perhaps aren't. So I started this episode speaking about Google's TPU. And I mentioned that you can't really mention AI hardware these days without having Google as part of that mix. That they've been one of the first to do it at scale, but they're in this unique position as a hyperscaler because they can run it on their own workloads.
Yeah, absolutely. They can just do whatever they want, basically. They know what their own workload is and they know exactly what they want to do and how to do it.
It's one of the things that we call silicon that you sell is merchant silicon, right? Whether that's x86, whether that's ARM, whether that's like a dedicated AI chip, whether it's a GPU, Google are in a situation where they don't have to do merchant silicon, right? If you know what workload you're running and you run it internally, that's fine. Okay, they have offered something in the cloud now. So there are some things you have to do like security and nearest neighbor, but with the TPU, you rent out a whole pod. You don't just rent half of one.
Sure, yeah, absolutely.
So, but I mean, 4 generations of chips, they tend to only speak about it, 1 year after it's been deployed. So even though they've just been speaking about V4 this year, they've probably got V5 and V6 is probably up and
running. I'm sure they have, yeah. That's unfortunately, they don't open their doors as much as some other companies, but they don't have to. They only use it themselves, so they don't need to sell it to us.
It's companies that don't need to sell are in that position where they don't need to speak to us.
Exactly, yes.
Which is frustrating from our point of view. It's like, tell us what you got.
Tell us your secrets.
Yeah. And I can't remember which conference it was. Last year, or maybe even pre-pandemic, I was at a Google booth, and they had one of their TPU V3s, one of their 4 socket systems or 4 chip systems, and it had all the liquid cooling because it's all liquid cooled and whatever. And I was there and I was looking at it, and a guy comes over and goes, "Oh, have you got any questions?" And I started asking some technical questions. And it's like, "Oh, who do you work for?" And then it's his media. And he's like, "I'm not meant to talk to you," and goes away.
This is what happens.
That happens.
This is what happens.
But Google also kind of introduced this concept of BrainFloat 16 support, BF.
That's right. This is kind of early on when we were looking at what number formats are the best, what data types are going to be the best for AI. AI, of course, the workload is evolving absolutely all the time. So at the time, BF16, they call it Brain Float 16, will look to be the optimum, but things change very quickly, as we'll find out.
Yeah. It's that mix of precision and range, but also the fewer bits you have, the more operations you can do.
Absolutely. There is some play in handling multiple precisions as well, which again we'll get to in another episode, but it gets more complicated. It only gets more complicated from here, right?
It's the whole topic of quantization, I think, requires a dedicated video on itself.
Probably, yes.
And a maths lecture and just don't start talking about posits because that's something else entirely. Yeah.
Okay, I'm out.
But so with the TPU, with the V4, and they've kind of also got like a V4 inference chip as well now. This was one of the first chips in the market where they actively promoted that they're using artificial intelligence to build the thing. So AI in chip design itself. So normally chip design, okay, you have transistors, but then you build them into macros, and then those build into libraries, and then you build your chip out of a combination of those. Each one is like an individual separate layer that you have experts that optimize for that in specific layer. And then you take your process development kit from the foundry, and then you decide, what libraries, what macros you can use, and what functions. Then you put them all together, and then you do what's called place and route, where software basically decides where all the wires go.
So it's automated. So some of the things we're talking about as a person doing it, some of these things are automated, right?
Well, if you've got a billion transistors, you're not got somebody going 1, 2,
exactly,
3.
Exactly.
Yeah. So with this tool, they were able to get into sort of like the macro level and find the best way to position certain blocks, to minimize wire delay, to maximize frequency, to minimize power. And you've spoken, like I have, with Cadence and Synopsys, and their whole thing is now how can we apply that in multiple levels?
It's very, very impressive what they can do now. But if you can save so much power, it's like, now I don't need to move to the next process node. So if I can use AI to accelerate the process that much,
get a free node,
basically. Super cool.
It was funny. I can't remember. I think it was us speaking to Cadence, and they said that their newest products even applies AI to the metadata of chip design, so they can detect when bad design is most likely to happen. Turns out it's Friday afternoon, right before.
Who knew?
It's like hospitals are better operations on a Monday morning than a Friday afternoon. But not only are we now using AI to make chips, we're using AI to make AI chips to make AI chips.
To accelerate designing more new chips.
Yeah,
yes. We've got this whole sci-fi scenario going on.
Is that a linear or is that like an exponential snowball?
I think we're small snowball right now.
Small snowball right now.
Yeah.
Right now. So Google is having some change up with its teams and its silicon. So now I have a couple of new friends in that area.
Maybe we can find out some more.
Maybe not. Maybe they're working on other chip products. They won't tell me yet. Yet being the key word.
Okay.
So also as part of this episode, Sally covered NVIDIA's, big selling.
Absolutely, the A100.
So why are we talking about A100 and not H100 right now?
Because it's the market leader. It's absolutely everywhere. If you're buying AI hardware in your data center or enterprise level, that's probably what you're buying today. Let's face it. NVIDIA have huge market share, and there are obviously good reasons for that, right? But yeah, GPU, effectively. This is, the flagship, basically the current generation. So I think it's important because this is the one that all other AI chips are measured against, right? If you're an AI hardware company, you're calling you and me saying, it's 2x the A100, or it's 100x the A100, or it's 100,000x the A100. I won't tell you who that was, but it's right.
Yeah, what in cost?
No.
Maybe. Whenever we speak to AI companies, obviously, if you're doing training, you're always comparing against NVIDIA.
Yeah, absolutely.
NVIDIA is the training leader.
Absolutely.
So NVIDIA have what is normally 90% of the market. So do you choose to build a chip that either competes against NVIDIA, who has multiple generations of software backing it as well, or do you go after the other 10% of the market where you've got 100 different companies competing for that, smaller portion?
I mean, it's a tough shout. I mean, NVIDIA doesn't have any inference-only hardware. They only make training and inference hardware, right? GPUs. So is it easier to make a more efficient design just for inference and then compete against NVIDIA that way? I think probably yes. But don't get me wrong, it's not going to be easy, right? NVIDIA have such a kind of a stranglehold on the market right now. I don't think it's going to be easy by any stretch of the imagination. NVIDIA's software story, of course, is so strong and so important with CUDA. I can't not mention CUDA at this point, right? Everybody already uses it, which is a huge part of its appeal. So you're up against that too, right?
NVIDIA has the roadmaps, right? How many startups have you spoken to? And they're like, yeah, we have a great chip. And okay, you have a great chip, but where's the next generation? Where's the money for the generation after that? How are you able to support at scale your new hardware? And it's telling when you have companies of engineers versus companies of marketers versus companies that have both, right? Because engineers will focus on the one, marketers will focus on the story, regardless of whether they've got the hardware or not, and perhaps get ahead of themselves.
I mean, ultimately, you're up against NVIDIA's billions and billions of dollars of investment in this sector. There's a reason they're the leader, right?
And
we're not to
decade.
I mean, it's a good story if we find an AI chip startup that is going to take on NVIDIA. But realistically, at this point, I'm not so sure.
I mean, we'll probably wax lyrical several times about the AI chip companies that will win out and those that will lose out. Every market goes through consolidation, M&A. I mean, how many AI startups has Intel purchased and how many still exist today? It's also that sort of thing, right?
Right, yeah.
So the fact, should NVIDIA continue to be the market leader? And it's maybe we might even start talking monopoly at some point. It's that weird thing, but I think I remember back in the day, back when they were launched, we were offered a review sample of the A100, either the 40 gig or an 80 gig, or even access to it. And as somebody who doesn't write AI software, right? Okay, I'm more of a chip guy than a solutions guy. You get it and you think, now what? Because they're still amazing bits of kit.
Absolutely.
It's, what was 600-700 square millimeters, how many billions of transistors. I mean, they even put 6 HBM2Es HBM2E on the damn thing, and one of them is disabled, right?
You couldn't handle that much memory bandwidth.
It's for redundancy, right?
Sure,
we get that.
Sure.
You have to have known good die and packaging, and that is still expensive. But to be almost blasé, but I mean, these chips have also led the way in power. I mean, what do they go up to now? 500 watts?
I'm
pretty sure I've seen them up at 600.
I've got the Hopper figure in my head, which is 700.
Yeah, and that's only ever going more and more. So
it only goes
more
up.
Than more.
Yeah, it only goes up from here.
Yeah, it's funny. I've been in some of those conversations lately where people have been talking about what's the real limit, right? Of not only the hardware but also a data center rack.
Sure.
Right?
Yeah, sure.
Because what's a standard rack? 5 kilowatts, anywhere from 5 to 10.
But then you need cooling and stuff as well, right? You have to deal with power in, power out. It's a lot.
And then obviously NVIDIA has DGX and HGX and all these combined systems.
Absolutely. So make it dead easy. Just pretty much phone up and say, I want to buy a supercomputer, AI supercomputer. You can just get it.
Here's $500,000.
Here it is. Here's millions. Here's my millions. And they just pretty much deliver it. It's all.
I think it was Supercomputing 2019. I saw a company called Lambda who sell HGX systems. They were offering a special, I can't remember if it was 10 or 20% off if you used a discount code before the end of the year.
20% off? How many millions is that?
Well, I think HGX at that point was something like anywhere from 300 to 500, depending on how you kitted it out. But yeah.
Quite a serious discount.
Yeah, it is. It is. And just buy a few more servers with the rest.
Absolutely.
Obviously not NVIDIA servers, but...
Well...
It's NVIDIA has so many AI hardware products now.
They do. They absolutely do. A100, the current gen, is kind of the flagship. We're looking forward to the Hopper, the next gen coming as well. But they have everything from like Orin, they have Jetson, they have edge solutions for autonomous vehicles. They have solutions for medical devices. They have all different kinds of products as well. So yeah, we're kind of talking about the A100 here as the flagship, but there's a lot more there.
Yeah, Grace Hopper next year.
Grace Hopper, yeah, CPU and GPU, same package. Super cool for supercomputers.
It's they've got a good naming strategy.
I do like it. I'm not sure if my company was called Ampere. Would I like that the generation was called Ampere? I don't know, but I like Grace Hopper.
Yeah, and there'll be a few more coming as well. So, this episode is sponsored by IBM. IBM has spent more than $2 billion on its AI hardware center, focusing on digital cores, analog cores, heterogeneous integration, and test-bed systems. If you're interested in getting involved in AI, either academic or commercial, then IBM's AI Hardware Center is a great place to be in order to combine both knowledge about hardware and software, full-stack solutions, all that lovely stuff. Plenty of videos on this channel have been sponsored by IBM about their AI strategy. I highly suggest you go check them out or click in the links in the video description below. So after NVIDIA, I spoke about IBM. And if you've been on my channel, as we're filming this sort of back end of Q4, there's been a little bit of IBM content coming out. Just so because I was there and they're a client of mine, obviously. But this whole AIU, I mean, the artificial intelligence unit on that video that I did there, a lot of comments were basically, IBM's in the AI hardware game. I mean, did you know about this chip before?
So I've known it's been coming for a while. I wasn't sure exactly what form it would take, but they already have demonstrated test chip kind of hardware, ultra low precision, and they also have IBM Telum, which we'll speak about in a future episode. So yeah, I guess we knew it was coming, but it's interesting to see the exact form factor, how many cores and stuff, exactly where they pitched it.
They've also got a company, Israel, that's licensing the IP, because that's the whole thing. I mean, IBM can sometimes be a complex company. It's like, how exactly are they making their money, and where is it coming from, and how do they have limitless bucket loads full? But it comes down to consulting. It comes down to things like hybrid cloud, and again, that also defines it depends how you define cloud. But having another inference chip on the market backed by a big player can be really important, especially with this ultra low precision stuff. I mean, their whole thing was, let's do inference on int 2. We've got instructions for int 2. I don't think any of the big chip guys are playing. Nobody
is really going that low right now. A couple of years ago, it was really fashionable to talk about binarized networks, which is 1 bit.
The int 1.
Yeah, which is super cool. But that kind of, haven't heard anything about that for a little while, so it makes me wonder, did it work? Like, what happened? But
research wasn't done yet properly.
Could be. But yeah, with the ultra low precision, you can save tons of power. You can massively increase the throughput.
As long as you keep the accuracy.
But it's the trade-off is accuracy, prediction accuracy of the results. So,
I mean, as we're filming this, I was just at Qualcomm's event, and they were talking about putting int 4 into the smartphone chips. So this is another stage beyond that, and as long as you don't start talking about int 2 sparse, and how many tops or pops or EOPs of that, right? So, I mean, IBM are still to put out speeds and feeds for this chip. They were very clear to me when I was handling it. This is still a prototype.
Yeah,
they haven't even finalized on the heatsink design, that sort of thing. So it's bring up of the hardware. I mean, the architecture is pretty nailed, and this is A0 silicon really. So we still got a way to go on that, and it's one of the arguments I put to IBM is are you ahead? Are you behind? And sometimes it's hard to tell with these companies.
It can be, especially because it's really difficult to get an apples to apples comparison. and then we get a lot of specmanship, shall we say, a lot of bullshit, quite frankly, as well. So it can be difficult to know exactly where we stand.
Or they pick and choose the metrics that
they absolutely pick and choose, and they absolutely do like theoretical max instead of what's a realistic amount of tops that I can get. So yeah, it's tricky.
Yeah, or even on the power side.
Right. Yeah.
Yeah. So, in this episode, we also spoke about AMD. I put AMD here because even though their chip, the MI250X, is mostly focused on HPC, some people do use it for AI. And
we've got a lot of AI in HPC nowadays, so there's a lot of crossover scientific computing, right?
We're seeing a lot of even supercomputing centers add to their clusters dedicated AI hardware.
Cool. Okay.
Right, which is, okay, so we're doing some big drug search. Let's reduce the search space on the AI supercomputer or the AI computer first, and then we don't need to wait months on the supercomputer itself, and we only need to wait weeks or days because we've eliminated half or more of the search space that we don't need. So it's having one piece of hardware to do both is nice.
Gives you that flexibility, like when you're designing your supercomputer, how much AI am I doing? How much scientific am I doing? Like, it doesn't matter then. You can just use the same chip for both.
It also simplifies it from the admin side.
Sure.
I've been speaking to a few of those admins, and users in general are stupid. HPC users apparently follow the same.
Is that right?
Yeah.
Okay.
So
like some of the smartest people in the world that we're talking about.
Well, I mean, I've spoken to chip designers who can't access their own email, right?
That's a specific type of person. That's not stupidity.
Oh, yeah. Well,
that's like academics, basically.
Yeah. It's they can visualize circuits in their head, but don't ask them to open an app on their phone or something.
Tie shoelaces. Yeah. No offense if you're watching. Sorry.
It's all right. They haven't even opened you.
No, okay. We're off the hook.
Yeah. But overall, I think this was a good way to start the show. We've covered a lot of key, pretty much all these companies I've been following since they've been announced. Interesting to see where they go to, having some of the big players who aren't necessarily revenue restricted, but then you've got, so Biren, for example, is a VC-funded startup. Absolutely. So actually, one thing we should, before we close out, speak about Biren, is some of the geopolitical situation.
Yes. This is a tough one. The Biden administration says no for supercomputer chips.
So just to bring everybody up to speed, we obviously a few years ago, during the previous administration, had the Entity List.
That's right.
Which stopped Chinese companies being able to manufacture chips at TSMC. The long and short of it.
Yeah, and stopped US companies shipping to certain entities.
Yeah. So we already there was already export limits in terms of performance.
Yeah.
And there's a document that lists all like the major CPUs, and they essentially rate their performance as listed frequency times by operations per second.
Yeah.
And that's how you scale. Obviously, with things like AI chips, that gets a bit more difficult. It was even difficult with CPUs versus GPUs, right? Because CPUs operate natively in a 64-bit format, whereas a GPU internally can, be 8 or 16-bit, and then you do your combination. AI, what happens if you have a hybrid floating point 8 format, right?
Which performance number are we choosing? That is the limit, right?
Yeah, or let's add sparsity into that mix as well.
Well, yeah, there's lots of other things you can do.
Fiddly things.
Yeah.
So Biren announced the BR100 earlier this year.
Yeah.
Earlier 2022, if you're seeing this in 2023, earlier last year. And they went through the architecture with us. There's a big presentation of hot chips, though technically they announced it before that. And it's just this dual chip design like AMD's MI250X, lots of HBM. And now the US is saying companies who are able to get chips made at TSMC aren't allowed to export those high-performance chips. And TSMC, you can't make them anymore if they're above a certain performance.
So even though Biren is a Chinese company, it can't ship its chips to Chinese companies. Yeah.
Yes.
That's the situation.
It can't get them made, and then it can't deploy them.
Yeah.
If they can get them made.
Yeah.
So in order to get around these, because there's issues in way that you can actually do the performance, they're actually derating the memory bandwidth.
There are different ways of doing it, but that's one of the performance limits,
Yeah.
I think. Yeah. So it's just like, let's turn that down a bit, and then it'll pass the regs, and everything's fine, right?
Well, I mean, so one of the big limiting factors in AI hardware today, especially in training, is memory bandwidth. Feed the beast. So this is why we have companies that have got HBM, HBM2, HBM2E, and even HBM3.
Yeah.
Because they just want to put in as much memory bandwidth as they can. Or with inference, it's LPDDR4, LPDDR5, and with some of the big, just standard CPU chips, it's DDR5 now. So if the US comes around and says you need to reduce your memory bandwidth, but you've already built the chip based on HBM, do you use less HBM? Do you run at a lower frequency? And this is essentially kind of what Biren is having to do, and others.
If I just run it at a lower frequency, will that meet the regs, or do I?
Right.
It's very bit of a grey area right now. Yeah.
Also, what frequency do you use?
Right.
Idle, active, overclocked, or do you ship it at a low frequency and you also bundle in this scratch off thing that has a code that unlocks the high frequency?
There could be some ways around it, I guess.
Yeah. Well, especially for the firmware update.
Yeah.
Right. It ships at 200 megahertz, firmware update to 400.
We promise we won't do the firmware update. Like, how is the US administering this? I don't know.
I mean, it's aggressive. It means that where there should be competition in the market, it's reducing that competition. I mean, regardless of whether your political affiliation with monitoring and everything else and all that, if we're just purely speaking from the fundamental physics and silicon and the reason why we're talking about this stuff, it's frustrating.
It is frustrating, and I feel like it's just giving a huge boost to Chinese companies. Say, go ahead and make your own chips now. Go and invest more money in making more AI chips.
Yeah.
It's better AI chips, which they will do, and it will be very soon.
And okay, so you can't do the big 700 watt chips. Maybe they develop better chiplet strategy. If they're limited to SMIC or UMC or whatever,
let's do chiplets.
Yeah, let's just scale out. Okay, we may not have the peak single core performance, but
just build a bigger computer. This is supercomputers we're talking about, right? Just build a bigger computer, more nodes. The chips that are only 80% as good. Just build a bigger computer. And
well, so this was a big thing actually with the top 500 list this year. People are concerned that China isn't no longer submitting results.
Yeah, they don't want us to know.
so I mean, okay, we get defense, right? And
sure.
But if China aren't submitting results or they're not updating the results that are already there, nobody can really gauge what level of performance they are. So last year in the Gordon Bell Prize, they had the Sunway system had 2 papers there.
Yep.
And I remember this big commotion about exactly what level of performance those supercomputers are.
Well, it's like, were we talking about 1 exaflops at the time? We don't know.
It was, because Top 500 measures LinPack, and which is FP64, dense matrix compute.
Yep.
Whereas what they were publishing was reduced precision.
Okay, so
in a different, but also scientific, not just pure matrix. So, yeah, it's the more I'm feeling, the more restrictions we get, the more of a smokescreen it is for us understanding what's going on.
I think it's definitely, our limited visibility into China is going to get much worse.
Yeah.
Unfortunately.
So if anybody watching this has deeper insights into the Chinese
please call us.
Yeah. And maybe we might get around to doing a China-only episode.
Yeah, that would be cool.
So, but let's put a plug in there. We've still got many more episodes to film this week. But big thanks to Sally for participating.
Thank you.
If you're watching this as it comes out, we're going to have another episode next week. If you're watching this afterwards, then just keep on rolling.